So we are finishing up section 2, and section 2 is on transforming and combining random variables. So we talked about how to transform a single variable, and then we talked about how to combine multiple random variables. And we've honestly gone through all the material, but I have a couple more examples just to kind of recap the whole thing. So, all right. Using all the rules together, here we go. Example 6. A large car dealership keeps track of sales and lease agreements made during each hour of the day. S will stand for the number of cars sold, so this is sold, and L stands for the number of cars leased during the first hour of business on a randomly selected day. Based on previous records, the probability distributions of S and L are as follows. And what I did here is I gave you the mean, the variance, and the standard deviation for each. And I said, if you want extra practice on how to do that in your calculator, there you go. You can punch those into your column 1, column 2, and would you be able to get all these numbers out? All right, but to save us some time, I gave it to you. On this page, all I want to do is kind of talk about how to interpret this, okay? And I chose we're just going to interpret mu for S and sigma for S. And you could do this something similar for the leasing as well. All right, so how we interpret the mean in the long run. In the long run, okay, after many, many cars are sold, in the long run, if one day is randomly selected, we would expect, and that's why we also call it expected value, we would expect the number of cars, and I'm doing S, so sold, during the first hour of business to be about 1.1 cars on average. And I said, be generous with those vague terms. If one day is randomly selected, we would expect the number of cars sold during the first hour of business to be about 1.1 cars on average. Sigma, your standard deviation, it means the same thing that it always has. Sigma is measuring the average distance from the mean. Okay, so we're going to start with some of the same phrasing though. We're going to say in the long run, if one day is randomly selected, the number of cars sold during the first hour of business will vary from the mean of 1.1 by about 0.94 car. 94/100th of a car. So half of what you're writing is just rephrasing the question. I would say about a third of it's rephrasing. About a third of it is all the general stuff about in the long run and all that. You know, so it's just kind of filling in the blanks there. You really could almost memorize that phrasing and just kind of fill in the blanks on a couple things. Okay. All right, you good with that? You got that written down? So you have your test. I don't know if you look at the calendar, but I think we could probably get to your test on the Thursday before the break. Or we could just wait and do it on Friday. I just didn't know how many of you were going to be gone on Friday if parents are pulling you out early, but We can talk more about that, but Thursday or Friday next week is going to be your test. All right, so now I repeated that same information here, so we don't have to flip our paper back and forth. And we are now going to practice our rules. So we are going to do the total cars sold or leased. So in other words, the total number of contracts that they made at this dealership. So we're going to do S plus L. And then we're going to talk about how many more were sold than leased, because in general, we seem to sell in higher quantities. Now, you could do L minus S, and you have negatives. You could do that, but we're going to do S minus L. So I'm defining two new random variables. Okay, this is going to be an example of, this is combining random variables. S and L are each a variable on their own, a discrete random variable, and we are now combining them to make T and D. So this is what I would expect you to be able to do on your test. If we want to find the mean and standard deviation for T. All right, so we're going to start with T is defined as S plus L. The mean, you can do exactly what probably intuitively feels right. If you want the mu for T, you can take the mu for S and add the mu for L. So we can take that 1.1 and we can add it to the 0.7 over there and get an answer of 1.8. So we could say in the long run, if one day is randomly selected, we would expect about 1.8 contracts to have been signed in the first hour of business, okay, whether they were sales or leases. Now, for standard deviation, remember, you can't add standard deviations. You can only add variances. And to be honest, very often this number won't be given to you. This number would not be given to you. So what you want to start by doing is set up something that looks like the Pythagorean theorem. So think about, we have sigma T would be sigma S plus sigma L. And you should look at that and go, no, I'm not allowed to do that. I got to make it look like the Pythagorean theorem. Sigma squared equals sigma squared plus sigma squared. Or better yet, if I take the square root of both sides, I'm going to scribble out this square and I'm just going to put this side under a really big square root. You can't take each square root separately. It's got to be the whole thing with the order of operations. So very often what this is going to look like, because like I said, you very often won't have this number, you would take the 0.94 and square it, plus you would take the 0.64 and square it, add them together, and then square root it. So you would pull out your calculator, and you would be able to do that in one step. The square root of 0.94 squared plus 0.64 squared. Make sure it's all written under a radical like that. 1.14. And you can interpret it the same way. If one day is randomly selected, okay, we would expect that the number of cars that were either sold or leased would vary from the mean by about 1.14. Okay. Now for subtraction, for D equals S minus L is what I defined it. And once again, for the mean, you can do exactly what feels right. If you want the mu for D, you can take the mu for S and subtract the mu for L, which would end up being 1.1 minus 0.7, which would be 0.4. And for the standard deviation for D, you might say, Mrs. Ferry, we ran out of room. You know what the standard deviation is going to be? It's going to be the exact same thing. I don't care if you are combining random variables through addition or subtraction. The standard deviation will work the same way. It should always be set up like the Pythagorean theorem. Okay, and that's what I had in this box right here in the notes, and in this box right here in the notes, Those formulas are not on your formula page. Okay, you need to know them. All right, so now what I want to get into is we're going to do some transforming and combining all in the same problem. Okay, so it says corporate office gives the dealership a $500 bonus every time they sell a car and a $300 bonus every time they lease a car. And A is going to stand for the total amount of money that they earn in bonuses. Okay, so I am going to start by setting up A mathematically. The amount of money, I get $500 for every car that's sold, so 500 times S, in addition to a $300 bonus for every lease, so 300 times L. So what I want you to be able to notice here is by itself, that is what we would call transforming a random variable. That would be transforming a random variable, but put it all together and we are now transforming and combining all in one problem. Now, I've been doing this. I said, this is my 7th year teaching this class. I don't do well in a problem that has transformations and combining in the same problem. I tend to mess up my rules, okay? What I like to do is I can see that that is a transformation. I set up a separate, and pick any letter you want. I'm just going to call it P. I'm going to set up P as 500 times S. That is all by itself a transformation. And I know my rules for transformations. Now you guys you're going to have to study this for your test, but the rules for transformations were, if you are multiplying, then you multiply the expected value and you multiply the standard deviation. If you're adding, you add the expected value, but you don't do anything to standard deviation. Okay, so you have to know the rules for combining versus transforming. So if I want the mu for P, I can do exactly what feels right. 500 times the mu for S. If I want sigma for P, I can again do what feels right. 500 times the sigma for S. Okay, so I would then say this is going to be 500 times the mu for S was 1.1, which that comes out to be 550. And this is 500 times sigma for S, which was 0.94, and I have that comes out to be 470. So I have now taken this and I just renamed it P. And now I'm going to take the other part of it and I'm just going to rename that Q. So over here, I'm going to say Q is being defined as 300 times L. And again, that by itself is a transformation. So I can figure out the mu for Q by doing 300 times the mu for L, which would be 300 times the 0.7 from up above. Oh my gosh, 0.7. And that comes out to be 210. And the sigma for Q is going to be 300 times the sigma for L, which was 300 times 0.64. These are running together. Let's separate that. And that comes out to be 192. So I do all my transforming off to the side. And then I come back here and say, okay, now I'm going to call A, instead of 500S plus 300L, I'm going to call A P plus Q. Because now I can apply just the rules for combining. And I'm going to say it again. You can't do it all in one step. Maybe you guys will end up better than I am at this. I just know every time I try to go from here to the correct answer, I mess up the rules. I like to separate transformations and now I'm combining. Because now if I want to find the mu for A, I know the rule is to take the mu for P and I can add the mu for Q. And I've done my work over here. The mu for P was 550. Plus the mu for Q is 210. So 760. And I will say, the means I'm usually okay on. It's the standard deviations I will mess up when I try to do all the rules at once. Because yeah, it's just the rules are, because they're different. Because over here, you literally can multiply with the standard deviations, but over here, you have to work from the variance. So now when I come back to say, what is the sigma for A? And you're going to be tempted to say, oh, I'm going to take the sigma for P and add the sigma for Q. And hopefully as soon as you write that on your paper, as you're writing, oh, wait, this is the one that has to look like the Pythagorean theorem. Or better yet, let's take away this square and put this under a giant square root. So my sigma for A is going to be sigma for P. Sigma for P was 470, but that needs to be squared. Plus the sigma for Q was 192, but that needs to be squared. And then a giant square root over that whole thing. So I would type in the square root of 470 squared plus 192 squared, 507.71.70, I guess. And I'm going to 2 decimal places there because this is dollars. This is the amount of money in bonuses. And again, the interpretation of this is, once again, in the long run, if one day is randomly selected, we would expect the amount of bonuses paid out in the first hour of business to be about $760. We would expect any one randomly picked first hour of the day, we would expect the amount of bonuses to vary from that by about $507. Okay, you can still interpret it the same way. Now, if you look at the mathematics that's going on here, this is where some of you might say, I don't need to do this like Mrs. Ferrari. I can put this all together. You could come back and look at it and say, where did the 470 come from? It came from the 500 times the 0.94, but that whole thing got squared. Plus, where did the 192 come from? Well, that came from 300 times 0.64, but that whole thing got squared. If you want to do it in one step and not have to show all the work separately like Miss Ferrari does because she's just too stupid to do in one step, okay, that's really the math that's going on here. So this right here is the rule for transforming, and it's been put inside of the rule for combining, okay? Now it says let B be the difference between the sale bonuses and the lease bonuses. So now I would say B is going to be equal to P minus Q. Well, we don't have a lot of work to do on this one, folks, because the mu is super easy. The mu really is just do it. Just do the subtraction. So it's going to be 550 minus 210. That's going to be 340. So in general, we would expect on average there to be a $340 difference between sales for or bonuses for sales and bonuses for leases. And what about the sigma for B? Why is there not a lot of work here? Because it's the same. If you're doing the same 2 random variables, I don't care if you're combining by adding or subtracting, it's going to be the exact same standard deviation. Okay, the rule is the same whether you're adding or subtracting random variables when you're combining them. All right, and then the last page, I switch us to thinking about normal distributions again. Okay, we got heights and weights, and now we're talking more, we have continuous random variables here. The cars were discrete. We sell one car, we sell two cars, we sell three cars. As soon as you start getting to things like heights and weights, we're talking about continuous random variables. Now, this says any sum or difference of normal random variables will also produce a new normal random variable. The apple example, okay? And I do the example with apples, but you could apply it elsewhere. This gets confusing for people because we're buying apples. We're buying lots of apples. So you just feel like it's one thing. We're buying one bag of apples. But you have to understand when that bag of apples is filled, every apple is its own random variable. We don't know what the weight is of each apple. So as we fill the bag, if every bag is filled with, does it say how many apples we have? Yeah, we have a dozen apples. Okay. Will every bag weigh exactly the same then because they all have 12 apples? Well, no. Even though the apples are all about the same size, we know some are bigger, some are smaller. So when they all get dumped into a bag, the weights of those bags are now going to be a new random variable. But what's going to happen is you're going to be very tempted just to say, well, if I have 12 apples, I can just do 12 times the mean of 9. If every apple has an average of 9, I would expect the average weight of the bag to be 108. And you're not wrong on that. But then what people want to do is they say, well, but then if the standard deviation is 1.5, I should be able to say that the standard deviation of this is going to be about 18. And that's actually not true. Because what actually happens here, and I'm going to call my new random variable S for the sum of the weights. If you want to call it W for weights, I don't care. Okay. But what you have to think about is if every apple is its own random variable, I'm going to let X equal the weight of one apple. So if I'm filling a bag with 12 apples, you might view that as apple 1 plus apple 2 plus apple 3, all the way up to apple number 12. And what a lot of people are tempted to do then is they just say, well, I'm just going to call that S equals 12X. And they say, oh, that's transforming a random variable. And no, it's not. It's actually combining random variables because every apple is its own random variable. You could think of it, if it makes you feel better, think of it as you're putting apples and peaches and oranges, and they're all going into the same bag. They just all happen to have the same need. What I do is I just number this as X sub 1, X sub 2, X sub 3, all the way to X sub 12 to remind myself that every X is really its own variable. This is an example of combining random variables. This is not just transforming by multiplying by 12. Now you get lucky on the mean because the rules end up being the same. Because technically what happens here, if I want mu sub s, technically what I have to do is mu sub x1 plus mu sub x2 plus mu sub x3 all the way up to mu sub x12. And it just so happens they all have the same mu of 9. So it's 9 plus 9 plus 9 plus how many 9s would I have? 12. And you end up with 108 ounces. And you end up with the same answer as the person who accidentally wrote that on their paper. Because coincidentally, the math ends up being the same. Where the difference comes in is when I go to do my sigma for S. For the person who does this incorrectly, they're just going to say, oh, mu sub S is 12 times 9. Sigma sub S is 12 times 1.5. You can't do that. The rule is you have to think about the Pythagorean theorem. You have to say the mu for S is actually sigma squared for x sub 1 plus sigma squared for x sub 2 plus sigma squared for x sub 3 all the way up to sigma squared for x sub 12, and it's all going to be under a giant square root. So now, when I plug in the sigma for x and square it, all right, it's going to be 1.5 squared plus another 1.5 squared plus another 1.5 squared, all the way up to, how many 1.5 squareds am I going to have? So here's the math that actually goes into your calculator right there. You do end up doing 12 times 1.5, but you actually end up doing 12 times 1.5 squared, and then you have to square root the whole thing. And this comes out to be 5.2. That is sigma sub s. Now, we haven't even answered the question yet, because the question says, what is the probability that the sum of the weights of all those apples is less than 100? I need to know, what is the probability that the sum is less than 100 ounces? And now we get into our notation again. I'm going to convert that into what's the probability that z is less than, and now we have to create a z value. All right, and this is why symbols and notation become important. I remind people, this is the number you're trying to convert. So that goes right here. But that is an S value. So when you do 100 minus the mean, you've got to do the mean for S. So we're going to use the 108. Divided by the standard deviation. And you have to do the standard deviation for S, which was 5.2. So I'm going to get negative 8 divided by 5.2. I have that comes out to be a z-score of negative 1.54. And then you would pull out your calculator and you would go back to your normal CDF. All right, so let's make a quick sketch on this. We have a z-score that's negative 1.54. It's going to be back here somewhere. And we want the probability that we are less than that. So my lower bound is going to be negative a gazillion. That's already there. My upper bound will be the negative 1.54. I've converted to z-scores, so leave the 0 and 1 alone. And that probability is 0.0618. So there's about a 6% chance that if a machine or if a person, people just randomly putting 12 apples in a bag, there is a 6% chance that when all is said and done, the bag's going to weigh less than 100 ounces, even though you'd expect it to weigh about 108 ounces. There's a 6% chance that you're going to get gypped a little bit and get only 100 ounces, if not less, for your apples. Last example. Suppose the height M of a group of males follows a normal distribution with a mean of 70 inches and a standard deviation of 3.5 inches. You know, these examples, I feel kind of bad because I steal these examples from different websites, or I wrote them a long time ago, whatever. And with all the gender, the non-binaries and things, I feel bad. Like all these examples are like traditional male, female, so I apologize. I don't mean to offend anybody. All right, so the height of a group of males is a normal distribution with a mean of 70 and a standard deviation of 3.5. For females, it's also a normal distribution, but as you might expect, the mean for a group of females is a little bit smaller, 65, and the standard deviation is only 3 inches. So it says, what is the probability that a randomly selected male is taller than the female? All right. So if we're talking about a comparison, this is where subtraction kind of makes sense. And I'm going to do the males minus the females because the males tend to be taller. You could reverse it, okay, and work in negatives, but why would you do that if you don't have to, okay? And I'm going to define this as D for the difference. Now, the way I set it up, I would expect males minus females. I would expect that to come out to be positive. Now, it actually could come out to be negative, but I would in general expect males minus females to give me positive. But another way to describe positive is I could say that males minus females will give me a result that is greater than 0, because that's another way of saying positive. So if I were to put this in notation, I would say, what is the probability that when I subtract, I get something that's greater than 0? I caution you on this because the 0, when you think about your typical z-scores, 0 is well within that range of a z-score, which generally runs from about -3 to +3. This is where notation becomes important, to realize that you still are not in z-scores, even though that's looking like it could be a z-score. You have to convert this to a z-score. And let your notation be a reminder. You are working right now in D. So I'm trying to convert 0. I have to subtract the mean. It's got to be the mean for D, and then you have to divide by the standard deviation, and it has to be the standard deviation for D. I have made a big deal about using proper notation. This is part of the reason, because you have to keep track of which mu do I want, because there's a mu for M, there's a mu for F. We need to create the mu for D. Well, that's easy enough to do because we know that the mu for D really will be the mu for M minus the mu for F, which would be 70 minus 65. So put a 5 right there. But the standard deviation for D, I don't care if you're adding or subtracting random variables. You have to take the standard deviation for the first one, square it, add it to the standard deviation for the next one, square it, and then take the square root of that whole thing. Don't square root each one separately. You got to do it all together. So you type into your calculator under one big square root, 3.5 squared plus 3 squared, 4.61. And that's what goes down here. So your z-score is going to be -5 divided by 4.61. So my z-score is -108. Again, give yourself a sketch. Dead center is a z-score of 0, so -108 might be like right about here. We want greater than that. So I'm looking for an answer that is well above 50%. And when I go to my normal CDF, the -1.08 is my lower bound. My upper bound is going to be some very large number. So about 0.8600. So what this is saying is, if I randomly select one male and one female from a group, if I just randomly select one male, one female, there is an 86% chance that the male is going to be taller than the female. What do you think? Reminder also, this is the work that I want to see if this is a free response. If this was a multiple choice, Remember, for multiple choice, you actually don't have to do all of this. If it's multiple choice and you don't have to show your work anyways, you could go to a normal CDF and you could say, I'm going to leave 0. And in your head, you just have to know I have not converted to z-scores. So you could use the mean of 5. You could use the standard deviation of 4.61. And you can get about the same answer. Okay? There have been years I haven't even shown that because I don't want you to get in that habit, because on a free response, this is what I want to see. But I also know that if you're on a multiple choice question, if you want to save yourself some time, then you don't have to go through the conversion process. You would still need these 2 numbers, however. Okay, you have to go through that work anyways. So, all right. So there's the end of 6.2. So tomorrow we'll take questions. And I think I have an exercise plan for tomorrow instead of diving right into the 6.3 notes. So we'll take questions on 6.2 and we'll do an in-class exercise. Only one more section. There's a lot of pages left though for one more section. 2, 4, 6. Oh my gosh, there's so many notes still. 6.3, I think I have on the calendar for 3 solid days again. So put on your patience caps. There's a lot in 6.3. It's pretty important stuff.